In the field of materials science, the phrase impossible material is not just a metaphor, but a concept that arises from the practical limitations of atomic structure and thermodynamics. Scientists use it to refer to materials that require a number of conflicting physical and mechanical properties to the point that they are theoretically impossible to coexist in an alloy system. A typical example is the requirement to have extremely high mechanical strength, maintain significant ductility at ultra-low temperatures, and withstand strong magnetic fields and high pressures. In practice, when the strength of a material is increased by restricting the movement of dislocations in the crystal lattice, the ability to deform plastically is often severely reduced, making the material brittle and susceptible to fracture. This phenomenon is even more severe at extremely low temperatures, where the thermal energy is insufficient to support the movement of dislocations, leading to brittle fracture instead of plastic deformation. This is why many heat-resistant steel alloys or arcanistic stainless steels, which are famous for their ductility at room temperature, quickly lose their properties when exposed to liquid helium at around -269 degrees Celsius. This challenge is particularly acute in the fusion energy industry, where superconducting magnets need to operate at extremely low temperatures and in huge magnetic fields. For example, the IDR project in France, one of the largest international fusion efforts, is using 316Ln arcanistic steel for its magnet support structures. Although 316Ln has been improved to be stronger and cold-resistant than conventional stainless steel, it still has its limits when subjected to enormous mechanical loads and strong magnetic fields for long periods of time. Cold embrittlement leads to the risk of microcracking, reducing the life of components and directly affecting the safety of the entire system. This is not only a technical problem, but also a barrier to the stable and long-term operation of new-generation nuclear power plants. Research groups around the world have tried many directions, from developing super-strong nickel-based alloys to improving the microstructure of stainless steel. But simultaneously achieving high yield strength, high ductility, good fatigue resistance, and stability under neutron radiation is still a distant goal. Therefore, the idea of creating a material that can withstand a magnetic field of 20 Tesla, a pressure of more than 1,300 megapascals, and still maintain an elongation of over 25% at extremely low temperatures was once considered impossible by many experts. In the field of materials science, this is considered a triangle of discord of mechanical properties, where each property, when optimized, will lead to a decrease in another property. The comprehensive combination of all three properties requires not only changes in the alloy composition, but also redesigning the microstructure at the grain level, and even the precipitation formation mechanism. This requires a multi-year development strategy that requires a combination of basic research, advanced metallurgy technology, and high-precision manufacturing capabilities, factors that very few countries have achieved so far. Therefore, when China announced that it had created CHSN-01 steel with parameters that exceeded the normal limits, the international scientific community was not only surprised, but also curious about how they had overcome this impossible problem. The CHSN-01 research and development journey began in 2011 when China was deeply involved in international fusion cooperation projects, especially IDR, and clearly recognized a technological gap. There was no steel material that could both meet mechanical strength and maintain ductility at extremely low temperatures for a long time. The problem was not simply about strengthening the alloy, something metallurgical engineers have been doing for decades, but how to strengthen it without making it brittle, especially when the operating environment is a harsh combination of liquid helium temperature, strong superconducting magnetic fields, and huge mechanical loads. The three technical requirements set for the research team were reaching a yield strength of about 1,500 megapascals, maintaining an elongation of over 25% at -269 degrees Celsius, and ensuring the ability to withstand a magnetic field of 20 Tesla without deformation or deterioration of mechanical properties. To solve this problem, the Chinese team adopted a rare materials development strategy, combining fundamental research on the deformation mechanism at the atomic level with alloy design at the nano-micro scale and continuous testing on industrial scale samples. In the first stage, they conducted atomic simulations and dislocation dynamics analysis to determine the root cause of the brittleness of existing steels at low temperatures. The results showed that, in extremely cold conditions, dislocation movement is almost completely inhibited, and stress concentration at grain boundaries becomes the starting point for cracking. This means that without changing both the elemental composition and grain structure, all efforts to increase strength by traditional methods will fail. From 2013 to 2016, the team tested dozens of alloy formulations, tweaking the carbon and nitrogen ratios to optimize the austenite network, and adding vanadium as a nanoprecipitation agent to anchor dislocations and prevent crack propagation. Each time, the steel sample was put through a rigorous series of tests: compression and tensile tests at -269°C, repeated loading tests for millions of cycles, and exposure to strong magnetic fields similar to a tokamak environment. In 2017, despite the fact that many international experts believed that improving the 316LN steel currently used at IDR was impossible, the team persisted in this direction, starting to optimize a multi-stage heat treatment process to simultaneously refine the grain and distribute the precipitates appropriately. By 2021, after nearly a decade, the target parameters were clearly defined: 1500 megapascals yield strength, elongation above 25% at ultra-low temperatures, and superior fatigue resistance. A consortium of 4 research institutes and 13 companies was formed to accelerate the transition from laboratory prototypes to industrial-scale products. This was not only a scientific challenge, but also a manufacturing challenge, ensuring uniform composition and microstructure across large batches, maintaining properties throughout the entire service life. Finally, at the end of 2023, CHSN-01 was officially born, not only meeting but exceeding the set parameters, marking 12 years of persistently overcoming the impossible problem of materials science.
To realize the idea of a steel that is both super strong and super plastic at extremely low temperatures, the Chinese research team relied on a series of breakthroughs in alloy composition design, microstructure control, and precision manufacturing process. In terms of composition, they did not simply maintain the austenite base as in traditional 316LN steel, but also restructured the elemental recipe to simultaneously control both strength and plasticity. The two elements, carbon and nitrogen, were adjusted at an optimal ratio to refine the austenite grain size, creating a more stable crystal lattice against low-temperature embrittlement. At the same time, vanadium was introduced as a microalloying agent, forming nanoprecipitates Vn or V,Cn finely distributed in the metal matrix. These particles act as anchors to hold the dislocations, preventing their free movement, thereby raising the yield limit without significantly reducing the ability to plastically deform. Along with the component design, the heat treatment process of CHSN-01 is also a significant step forward. The material undergoes several heat treatment stages, starting with a uniform annealing to dissolve all the alloying elements, followed by a flash annealing to freeze the ultrafine austenite structure, and finally a controlled aging to trigger the formation and stabilization of nanoprecipitates. It is this combination of grain refinement and precipitation control that enables CHSN-01 to simultaneously achieve extremely high strength and remarkable ductility, even at -269°C. Another issue that scientists had to address was the effect of strong superconducting magnetic fields on the material. In a tokamak environment, a 20 Tesla magnetic field creates very large Lorentz stresses, which can cause residual strain or trigger microcracks. To counteract this, the team applied a high-precision cold deformation rolling technique, which creates a uniformly oriented grain structure. This structure distributes stress more evenly and limits stress concentrations, the main cause of failure under harsh conditions. In addition, rolling and heat treatment parameters are calculated so that the amount of residual strain is at an optimal level, enough to increase the density of dislocations, strengthen, but not exceed the threshold of brittleness. Thanks to the combination of knowledge of material physics at the atomic level and manufacturing technology at the industrial scale, CHSN-01 has achieved a microstructure by design. This is a clear demonstration of the new trend in materials science, not only searching for new alloys by traditional trial and error, but also predicting and programming properties right from the design stage, ensuring that the final product meets the desired mechanical and physical parameters in the actual operating environment. When mechanical and physical testing was completed in late 2023, CHSN01 demonstrated a set of specifications that caught the attention of the material science community. First of all, the alloy's yield strength reached approximately 1,500 megapascals, which is about 2.5 times higher than the 316 Ln austenite steel currently used in ITER's superconducting magnet structure. This is an indicator that the material can withstand very large loads before plastic deformation occurs. At the same time, CHSN01's elongation still exceeded 25% at liquid helium temperature, minus 269 degrees Celsius, an extremely rare property because most steels lose their ability to deform when they reach high strength in deep cold conditions. This ability to maintain ductility means that the material does not suddenly collapse into brittle failure, but still absorbs deformation energy, improving operational safety. In addition, CHSN01 can withstand superconducting magnetic fields of up to 20 Tesla without any residual deformation or significant mechanical degradation. The 20 Tesla level is not only much higher than the minimum requirements for current tokamak magnets, around 12 to 15 Tesla, but also opens up the possibility of miniaturizing the device or increasing the magnetic field power in the future. The ability to withstand compressive pressures of up to 1,300 megapascals also shows potential for use in structures that are subject to strong compressive forces and vibrations, such as supports or enclosures for superconducting systems. Another impressive feature is the material's fatigue resistance. Tests have shown that CHSN01 can withstand more than 10 million load cycles at extremely low temperatures without developing microcracks, 2 to 3 times better than 316 Ln. This is a decisive factor for longevity in harsh operating environments where components are subject to vibrations and constant load changes. In addition, long-term durability measurements under neutron irradiation, simulating the environment inside a fusion reactor, showed that CHSN01 has significantly higher microstructural stability than conventional steel alloys. The combination of these parameters places CHSN01 in a very rare group of super-strong materials that can operate stably at mechanical and physical limits that previously only existed in theory. It not only surpasses the limits of the materials currently used in ITER, but also sets a new benchmark for the design of materials that can withstand deep cold, strong magnetic fields, and high loads. With such properties, CHSN01 not only solves the problem of materials in fusion, but also opens up the possibility of applications in aerospace, high-field magnetic resonance medical devices, and next-generation superconducting technology.
With its outstanding features, CHSN01 is quickly positioned as a strategic material in many cutting-edge technology fields, the most prominent of which is fusion energy. The most important and urgent application is in BEST, Burning Plasma Experimental Superconducting Tokamak, the artificial sun project developed by China, expected to create the first plasma in 2027. In the tokamak structure, the superconducting magnet coils not only need to maintain a strong, continuous magnetic field, but also have to withstand the enormous mechanical loads generated by plasma pressure and Lorentz force. The support frame and connecting parts of this system must operate at liquid helium temperatures, where most traditional materials quickly become brittle. Using CHSN01 in these locations significantly reduces the risk of fracture, extends operating life, and allows for a more compact yet stronger system design, thanks to its load-bearing capacity far exceeding current standards. In addition to fusion, CHSN01 also opens up great potential in space science. Space structures, especially unmanned exploration vehicles sent to the deep solar system or interstellar medium, are often subjected to near absolute zero temperatures and extreme temperature fluctuations when exposed to sunlight or in darkness. The ability to maintain both strength and flexibility under such conditions make CHSN-01 an ideal candidate for spacecraft frames, instrumentation support systems, and components of ion or magnetic engines. In the field of energy infrastructure, CHSN-01 can be integrated into superconducting power transmission systems and particle accelerators. Superconducting lines require conduits and supports that can withstand high mechanical forces, extremely low temperatures, and strong magnetic fields for long periods of time. Similarly, particle accelerators such as the Large Hadron Collider (LHC) operate under harsh conditions that CHSN-01 can fully meet, thereby increasing operating cycles, reducing maintenance time and component replacement costs. Equally important is the potential for high-tech medical applications. Newer generation magnetic resonance imaging machines, MRI, tend to use stronger magnetic fields to improve image quality and scanning speed, which means higher requirements for structural materials. With the ability to withstand 20 Tesla while maintaining mechanical stability, CHSN-01 could play an important role in MRI magnet supports, making the equipment operate more safely and last longer. In general, any field that combines extremely low temperatures, high loads, and strong magnetic fields is a potential playground for CHSN-01, transforming it from a solution for fusion to a versatile material platform for 21st century technology.
The birth of CHSN-01 is not only the result of a single material project, but also has profound implications for science, technology, and global energy development strategies. Scientifically, CHSN-01 is a clear demonstration that the boundary between possible and impossible in material science is not absolute. Previously, the combination of ultra-high mechanical strength, high ductility at extremely low temperatures, fatigue resistance, and strong magnetic field resistance in a single material was considered an intrinsic mechanical contradiction, almost impossible. The success of CHSN-01 shows that when combining fundamental research at the atomic level with precision microfabrication technology and optimized manufacturing processes, these limits can be completely broken. This opens up a new approach to material design. Instead of improving individual properties, scientists aim to optimize multiple properties simultaneously by programming the microstructure right from the design stage. From a technological perspective, CHSN-01 creates a new standard for materials that can withstand deep cold and strong magnetic fields, surpassing the decades-old 316 LN steel standard. Owning such a strategic material exclusively helps China not only ensure technological sovereignty in domestic fusion energy projects, but also create a strong bargaining position if it participates in supplying materials for international programs such as ITER or DEMO. In particular, because CHSN-01's applications range from energy, aerospace, superconducting infrastructure, to high-tech medicine, this steel can become an industrial platform, similar to the way titanium alloys or carbon fiber composites have shaped the civil aviation industry. The impact on clean energy is also key. Fusion has long been seen as the holy grail of energy, providing virtually endless, safe, CO2-free electricity. But to be commercialized, reactors need materials that can withstand decades of operation in harsh conditions without failure. CHSN-01, with its superior fatigue resistance, stability under neutron radiation, and performance at extremely low temperatures, is one of the building blocks that will make this dream a reality. In other words, it is not just a technical advance, but also a stepping stone to humanity's energy revolution. In the long term, CHSN-01's success will also spur research programs on custom materials,
where technical requirements are defined in advance and materials are reverse engineered from those requirements. This is the future of material science, promising new alloys and compounds for technologies we cannot yet imagine. In this context, CHSN-01 will probably be remembered not only for its impressive technical specifications, but also because it marks the moment when humans began to actively rewrite the rules of the game in material science.
Despite its impressive technical specifications and wide application potential, CHSN-01 still leaves many open questions that the scientific and engineering community needs to continue to find answers to. The first and most important challenge is the long-term durability under high-intensity neutron radiation. In the environment of a fusion reactor, the material will be continuously bombarded by high-energy neutrons, causing microstructural changes such as grain swelling, reduced ductility, or the formation of brittle phases. Although initial tests show that CHSN-01 is much more stable than 316 LN steel, there is no complete data on its behavior after decades of continuous operation. This is a key factor in determining the true life of the alloy in commercial fusion applications. The next question concerns the possibility of mass production at reasonable costs. CHSN-01 is developed through a sophisticated metallurgical process, including elemental composition control at the ppm, parts per million level, and complex multi-stage thermomechanical treatment. The precise reproduction of microstructures on an industrial scale requires a highly precise and synchronized production line, which is not common even in advanced steel mills. Without solving the problem of cost and reproducibility on a large scale, CHSN-01 will have difficulty becoming a popular material outside of strategic projects. Another issue is the ability to expand applications to new fields. In theory, the mechanical and physical properties of CHSN-01 are very suitable for aerospace, nuclear submarines, or next-generation medical superconducting systems. However, each industry has its own requirements in terms of mass, machinability, corrosion resistance, or magnetic compatibility. Determining and demonstrating that CHSN-01 meets all these requirements requires further interdisciplinary research, from material science, mechanical engineering, to life cycle assessment. In addition, there's still a gap in understanding the micromechanisms that enable CHSN-01 to simultaneously maintain strength and ductility at extremely low temperatures. Although researchers have identified the role of vanadium carbon nitrogen nanoprecipitation and ultrafine grain structure, the detailed interactions between these factors under complex loading conditions have not been fully characterized. Understanding this mechanism will not only help optimize CHSN-01, but also pave the way for the development of a post-CHSN-01 generation of materials with even higher performance. It is these unanswered questions that increase the scientific appeal of CHSN-01. It is not only a completed achievement, but also an open problem that stimulates the curiosity and creativity of the global material science community, promising to lead to many new discoveries in the coming decade. CHSN-01, in many ways, is not only a new type of steel with a set of technical parameters that exceed the standard, but also a demonstration of a new approach in material science, intentionally designing microstructures to achieve features that were previously considered contradictory or impossible. This appearance shows that humans can completely proactively program the properties of materials right from the idea stage, instead of depending on existing alloys and gradually improving them according to the traditional trial and error method. This is an important shift, paving the way for a new generation of materials that are ordered to serve specific technologies from energy, transportation, medicine, to space exploration.
In the field of energy, especially fusion, CHSN-01 can be considered a foundation brick to build the technological infrastructure of the future. Fusion promises virtually limitless, safe, CO2-free energy, but the biggest hurdle is the materials. The components must survive and operate reliably for decades in harsh conditions that few materials can withstand. CHSN-01, with its ability to resist fatigue, extreme cold, strong magnetic fields, and radiation stability, has gone a long way toward removing that barrier. If projects like BEST or future demo reactors succeed, this material will play an irreplaceable role in turning fusion from a scientific dream to a commercial reality. From a strategic perspective, mastering CHSN-01 also means gaining an advantage in the global supply chain of high-tech materials. The country that owns it will not only be confident in implementing domestic projects, but can also become the sole supplier for applications requiring special standards. This places CHSN-01 in the same category of critical materials as titanium alloys in the aerospace industry or nickel superalloys in gas turbines. More importantly, CHSN-01 marks a psychological milestone in the scientific community. The impossible boundary can be erased with enough data, simulation tools, and long-term commitment. It reminds us that scientific progress comes not only from random discoveries, but also from decades of persistent projects where scientists dare to pursue a seemingly impossible goal until they make it a reality. When we look back on this journey in the future, CHSN-01 may be seen as a symbol, the moment when humans began to actively shape matter as they wished, opening a new era of material science and technology.